So today we're talking about three different discrete probability distributions that show up really commonly. And their names are the binomial distribution, the Poisson distribution, and then we're going to talk again about the discrete uniform distribution. So first, the binomial distribution. When does this distribution show up? One example is, imagine you're going to the basketball court and you practice shooting free throws. Every time you make a free throw, you record a little tally mark in your notebook. A Bernoulli trial, and you should know this vocabulary word, named after a mathematician named Bernoulli. A Bernoulli trial is one iteration of a random process that could either be a success or a failure. So every time you attempt to shoot a free throw is a Bernoulli trial, because you're either going to succeed and make a basket or you're going to fail and you're not going to make a basket. If we define a new random variable to be the sum of all your Bernoulli trials, that is a binomially distributed random variable. We say the random variable follows the binomial distribution. So in this example, the number of free throws that you actually make after you attempt shooting like 10 free throws, that would be a binomial random variable because it's the sum of 10 Bernoulli trials. So when you see this or something like this show up in a word problem, you can think, I'm going to have to use the binomial distribution. The probability mass function, or this is oftentimes abbreviated PMF, of the binomial distribution is a function that tells you what's the probability of getting a specific outcome. Keeping my example going, if we're shooting free throws, and I have 10 attempts, I would say n is equal to 10. So the lowercase n is the number of attempts, the number of Bernoulli trials that are part of my experiment. So I should write that somewhere maybe. N is equal to the number of Bernoulli trials. K, when it shows up in this formula, is the specific outcome we are asking about. And then the P in this formula is the probability of success for each individual Bernoulli trial. So the probability mass function, the PMF, says the probability that my random variable is equal to k, which might be 5 or 7 or 10, right? Whatever number you're concerned about. The probability that you get that specific outcome is equal to n choose k times p to the k power times parentheses 1 minus p raised to the power n minus k. Because if I were to be talking about n equals 10 different attempted free throws, and I want to know what's the probability that I make exactly 5 free throws, this n choose k, that binomial coefficient, is going to be 10 choose 5, because there's 10 choose 5 different ways that I could make 5 out of 10 free throws. Maybe I make 5 in a row, and then I miss 5 in a row. Or maybe I miss 5 in a row and then I make 5 in a row. Or maybe I make all of the odd numbered free throws or make all of the even numbered free throws. But there's a bunch of different ways you could do that. And to count how many different ways there are, I would use n choose k to count how many possibilities. Then where you see p raised to the power k, that is part of the probability multiplication rule, where I'm multiplying p, the probability of success, k times, because I'm looking for k successes. And then the next part, 1 minus p, is the probability of failure. And then n minus k is the number of failures I'm looking for. And so that is the whole formula for getting an exact number of successes in a binomial experiment. The next thing here says the cumulative distribution function, which is abbreviated CDF, is a function that tells me what's the probability that my random variable is going to be less than or equal to a specific number. Okay? That's the difference. Is PMF is talking specifically about what's the probability my random variable is equal to a specific outcome. But the CDF is telling me what's the probability that my random variable is less than or equal to that specific outcome. And this notation looks a little bit crazy, but just remember the capital Greek letter sigma is telling me to add up a bunch of stuff. What am I adding up? Well, it looks exactly the same, right? I'm adding up the probabilities of getting every number of outcomes up to k, right? I'm just taking, all right, I want the probability of getting less than or equal to 5. So I'm going to add up the probability of getting 0 plus the probability of getting 1 plus the probability of getting 2 plus the probability of getting 3 plus the probability of getting 4 plus the probability of getting 5. And when I add up those together, I get the probability of getting less than or equal to 5. That's what the capital Greek letter sigma is saying. But like it says in the next line of my notes, we're not going to sit here and add up all of those terms, because that would take a long time, right? What can we do instead to make things faster? We're just going to use the table I passed out. So everybody has a table, and I need one of them. I should have kept one. Thank you. Everybody has a table that says binomial distribution CDF on top. And you've got to sort of become familiar with this. I'll draw it. Actually, I'll just open it up in Excel so we can all point at the TV and see it together. And find where I put that. Binomial distribution CDF table. So if you're wondering, how do I figure out the number of attempts? How do I line up the number of attempts? There's a bunch of little subtables in here. And above them, you see a little floating things that say n equals 8, n equals 7, n equals 9. That's the number of Bernoulli trials, the number of free throws you're attempting. Along the left column, this is the probability of success for each individual Bernoulli trial. That's your lowercase p. So if you've got a 50% chance of making a free throw, you would look at this row where you have a 0.5. So look up. And then the k, what specific value k am I looking for? That is the column number. So across the top, you've got k equals 0, k equals 1, k equals 2, 3, 4, 5, 6, 7. I don't have k equals 8 because I'm trying to save space on these tables that I pass out. And if there are 8 attempts and you're finding the CDF for k equals 8, what's the probability that you make 8 or fewer? The probability should be 1, right? That's adding up all of the probabilities together. So it should add to 1. So I'm only really concerned with k values between 0 and 7, because that's when I'm not necessarily going to get 1 for my answer. I'll show you an example of how to use this table here in a minute, but that's what I'm talking about. You don't actually have to use this formula. You can just use the tables, but you might actually have to use the PMF formula. Potentially. So that's the one to have written down on your notes sheet going into the next test. You really don't need to write the CDF down, because I'll let you use the table on the test. So you don't need to write this down. You can always use Microsoft Excel to find the PMF or the CDF of a statistical probability distribution function. This is how you type it in for Excel if you ever need to do that. The measures of central tendency, and by that I'm talking about the distribution mean, the distribution median, the distribution mode, are these. You can find the mean by multiplying the number of attempts times the probability of success. And hopefully that makes sense. If I attempt 10 free throws and my probability of success is 0.5, then I expect to make 5 out of 10 free throws. That's what I calculate. The median is the same thing, but we round down, or round in general, just round to the nearest number. That should be the median. The mode is what I get if I do n plus 1 times p and then round down. That should have the highest probability of any particular outcome. And then the measures of dispersion, well, here's my variance. The lowercase Greek letter sigma squared is variance. And then the variance is going to be n, the number of attempts, times p, the probability of success, times 1 minus p. So it's the attempts times the probability of success times the probability of failure. And then the standard deviation is, of course, just the square root of the variance. And that's always true for any binomial distribution. I know that's a whole lot, so if you didn't have a chance to copy all of it down onto your notes sheet, you might go back later and look up my lecture notes on the website, and that way you can have more time to copy this down. The next distribution I want to talk about is called the Poisson distribution. If anybody took a French class, what does Poisson mean in French? Fish. And believe it or not, this is not actually named after one application of it, but it's actually named after a mathematician whose last name was Poisson. It's like his last name was Fish. But the way I remember this distribution is with this example. The Poisson distribution would be relevant if you wake up early in the morning and you go fishing and you start to wonder, how many fish am I going to catch today? Maybe you have an expectation and you say, I expect to catch about 10 fish every time I go out to catch fish. So that's kind of like my expectation. But if I ask, what's the probability that I'm going to catch a specific number of fish today? Like, what's the probability that I'll catch exactly 10 fish? Or what's the probability that I catch exactly 9 fish or 15 fish? We can calculate that. We say that this is a random variable because we don't know what it's going to be until the end of the day when we count the number of fish in the cooler. But this is a Poisson distributed random variable. The PMF of the Poisson distribution is this: the probability that the number of fish I catch is exactly k is going to be equal to lambda raised to the k power times e to the power negative lambda divided by k factorial. Lambda is the expected number of fish that I would typically catch. K is exactly the number I'm asking about. E is 2.718. It's Euler's number.
Writing which one is which again?
Which one is which?
Yeah, like you did the other one where you were like P equals this.
Oh, yeah.
If you mind.
I can do that.
What each one represents?
So K is, what's the number I'm asking about? In other words, what's the probability that my random variable is exactly equal to K? Lambda is my expectation. How many do I expect to get on a typical day? So then, just like before, the cumulative distribution function has that capital Greek letter sigma because it means I'm adding up all of the probabilities for every outcome less than or equal to a specific outcome. So once again, you should know this one. You should put this PMF formula on your 8.5 by 11 page of handwritten notes front and back that you can bring in for your test. You should write that down, but you don't really need to know the cumulative distribution function. You're not going to actually use that. What you're going to use instead is that table that I just passed out, the table that says Poisson distribution CDF. That's the table you're going to use. And we'll do an example here in a minute, but I want to pull that up too, so you have it ready. This is what the Poisson distribution CDF table looks like. Across the top, you've got different values of lambda, so different expected outcomes. All across the rows, the row numbers are k's, like the exact probability outcome you're asking about. And so if you look up with the right lambda and the right k, you get the probability of that outcome given that expectation. Oh, sorry, I lied. That's not the probability of that outcome, it's the probability of getting that outcome or less, right? Because this is a CDF table. And the CDF is the probability of less than or equal to. So when you look up on the table, the CDF table tells us the probability of less than or equal to. So just like with all of these, there are Microsoft Excel commands that you can use to get the PMF and the CDFs really quickly and easily. The measures of central tendency for a Poisson distribution are these: mean, median, and mode. The mean is the expectation, and the expectation is my lambda parameter, and so that's easy. The median is not quite so easy. The median is still pretty close to the mean, but it's got kind of a crazy formula. We take lambda plus 1/3 minus 1/50 lambda, and then we round it down. But that's almost always just lambda for this class. The mode is going to be lambda but rounded down. And so if your expectation is 4.5, then we say the mode is 4. We're going to round down in case we have a lambda that's in between whole numbers. What about the measures of dispersion? Well, the variance is also lambda. By the way, this is a lowercase Greek letter lambda. And the standard deviation is like it always is. The standard deviation is always the square root of the variance. Okay, questions? Yeah, question? That's a Greek letter, like from the Greek alphabet. Like alpha, beta, gamma, delta, epsilon, blah, blah, blah. Yeah, that's just one of the Greek letters. And mathematicians sometimes use Greek letters because we run out of English letters to use to represent variables. So you got to keep coming up with symbols. And that's the next group of symbols. Yeah.
What do you mean by round down?
Round down means like, I'll give you an example. If I were going to round the number 4.9, that would be 5. But if I were going to round down the number 4.9, that would be 4. So any numbers that are caught between whole numbers would just get moved down to the nearest whole number less than that number. Good questions. Okay, so the last distribution we're going to talk about in terms of the discrete distributions is the discrete uniform distribution. We kind of started talking about this last time too. But if you open up Excel and you type in the command rand between, that's going to give you a random number between 5 and 12, including 5 and 12 as possibilities. And the same probability gets assigned to every single possible number in that range. So that's what makes a discrete uniform distribution. Uniform means it assigns the same probability to every outcome. If you want the probability mass function, the PMF of a discrete uniform distribution, the PMF is 1 divided by b minus a plus 1, where a is the least number possible, and b is the greatest number possible. From my uniform distribution. And there's no CDF table for the uniform distribution. And so if you need to get the CDF of a, oh shoot, that's a typo. I gotta fix my typos. That's not binomial, that's discrete uniform. Yeah, so if I need the CDF, I actually have to have this formula written down too. And another way you might see this occasionally is people will count the number of possibilities, and the number of possibilities would be b minus a plus 1. And so you might sometimes see the PMF written like this. And you might sometimes see the CDF written like this. But in that case, the lowercase n is saying how many possibilities are there? Just alternative ways to write the same thing. So again, we can have shortcut formulas to give me the mean, median, mode, and variance. The mean and the median are a plus b divided by 2, a plus b divided by 2. The mode does not exist for a discrete uniform distribution because, again, uniform means every outcome has the same probability. The mode of a distribution is saying which outcome has the greatest probability, and so that just doesn't click, right? There's no mode for a uniform distribution. But there's the mean, there's the median, and there's the variance formula. And again, if we chose to say n is the number of possibilities, then this variance formula is alternatively just n squared minus 1 over 12. And again, the standard deviation is the square root of the variance. And the goal here is to say, you know, last time we talked about discrete distributions in general, where we had like a countable number of outcomes and we could assign probabilities to those. And last time, for generalized discrete distributions, we calculated these things like mean, median, mode, variance, standard deviation. The formulas are longer if they don't fit into a nice category. But today, we're taking a look at 3 common categories of discrete distributions and writing these shortcut formulas so you don't have to go through the long process like you do if you catch a discrete distribution out in the wild. If you know it belongs to binomial or Poisson or discrete uniform, well, then you can just apply these formulas instead of doing the long, hard process. Yep, it is. Thank you for catching these because it makes it better next time I teach statistics.
Is it always 12?
Yep. Yep. And you know, if you've got questions, like maybe you're a really curious, maybe you're a very curious statistics student and you're like, man, why is that 12? I don't understand why the number 12 should show up in the variance of a discrete uniform distribution. Wikipedia conveniently has Wikipedia pages for everything that we're talking about today. So if you want to learn more about the discrete uniform distribution, click on that. And we're not going to talk about this in class, but you could eventually find, oh, I thought they would have a proof for the variance. Weird. So they have the variance here, but normally Wikipedia is good enough at providing proofs. Well, okay. There you go. So it's on the Wikipedia page for variance, that n squared minus 1 over 12. So you can kind of see where it shows up. But anyways, we're not going to do that in class. That's not our concern. We just need to know how to use the formula. So here's exercise number 2 on your homework. It says, suppose you decide to execute a quantum physics experiment. And one of the things about quantum physics is that it's not very deterministic, like the way that Newtonian physics works. Quantum physics only gives you probabilities of observing particular outcomes, which is nice for a statistics class. And suppose for this experiment, we expect a 25% probability of detecting a photon. You carry out 13 trials. What's the probability of detecting a photon 0 times? Here's how to think about this question when you see this question. I'm carrying out a number of trials for which there's a sense of having a success. Let's call it a success if we happen to detect a photon. And if we do not detect, let's pretend that's a failure. Then these become Bernoulli trials, where a Bernoulli trial is just a case where you've got a success or a failure and there's a probability of either one. This time the probability of success is 0.25. And the random variable that I'm concerned about here is the number of photons that we end up picking up on out of 13 trials. That's the sum of Bernoulli trials. And if a random variable is the sum of several Bernoulli trials, we say the random variable is a binomial random variable. So if this is a binomial random variable, then the probability that I get exactly 0 is going to be what happens when I apply the binomial probability mass function, where n is equal to 13 and k is equal to 0 and p is equal to 0.25. And if you don't remember, the binomial probability mass function says n choose k times p to the k power times 1 minus p to the power n minus k. And also, if you don't remember from a week ago when we were counting things, maybe not a week ago, I think it was Tuesday of this week. On Tuesday of this week, we were counting things and we said, well, n choose k is n factorial divided by k factorial times n minus k factorial. So we're talking about 13 factorial divided by 0 factorial times 13 minus 0 factorial times 0.25 raised to the power 0 times 1 minus 0.25 raised to the power 13 minus 0. So I'll end up with 13 factorial divided by 13 factorial, which is, because 0 factorial is 1, by the way, if you didn't know. So 13 factorial divided by 13 factorial, that's just 1, times 0.25 raised to the 0 power, that's just the number 1. 1 minus 0.25 is 0.75, and we're raising that to the power 13 minus 0, so raised to the power 13. 0.75 raised to the power 13 is 0.02376. Somewhere around that number. It's like a 2% probability. And that's the answer to this question here. It's also kind of the answer to the question, what's the probability of detecting a photon 13 times? Because I'm talking about getting a specific outcome for my binomial random variable. And if I want a specific outcome, I use the probability mass function. So this time, I have to use the same probability mass function with the same formula. Again, copy that down onto your page that you take in for your test, your page of notes. Because you're going to end up using it on the test. I want the probability that I get exactly 13 So I look to the binomial PMF function where n is 13, k is 13, and the probability p is 0.25. What's the probability of detecting a photon 5 times? Same deal. N is equal to 13, k is equal to 5, p is equal to 0.25, and we use the same formula. Okay, what's the probability of detecting a photon 5 or fewer times? The important part here is we realize the probability of getting 5 or fewer looks like this. And that is the binomial CDF, cumulative distribution function. And if I have something like this, where I need the CDF to get the probability that x is less than or equal to 5, I don't have to use a formula. This is easier in a way. I just have to pull up the table. Okay? So let's pull up the binomial CDF table, where n is 13, k is 5, and p is 0.25. And here it is. N is 13 means I'm looking at this part of the table. K is 5 means I'm looking at this column right here. And then P is 0.25, so I'm looking right here. And my answer is going to be 0.9198. That's how we look it up. 0.9198 is what you should find on that binomial CDF table. There's a 92% chance that you're going to detect one 5 or fewer times. Yep. It's right here. And that table is two-sided. So you might have to flip it over to find the n equals 13 table. But k is the column numbers and p is the row numbers. Next question, what's the probability of detecting a photon 3 or more times? So 3 or more means I'm looking for the probability that x is greater than or equal to 3. And this is a trick question. It's a very tricky question. Because you need to be able to recognize that that is the complement of the probability that x is less than or equal to 2. I'll say that again. The probability that x is greater than or equal to 3 is the complement of the probability that x is less than or equal to 2. Because x either has to be greater than or equal to 3 or less than or equal to 2. So when I add those two probabilities together, they have to add to give me 1. And the complement rule says that I can rewrite this probability as 1 minus that probability. And now that I have a probability in terms of like x is less than or equal to 2, that looks like a CDF probability. And so I use the CDF, where k is 2, to give me that number. And the CDF is nice and easy. I just have to look that up on the table. That's going to be k is 2, p is again 0.25, and so this is the number that I'm looking up now. Because n is 13, k is 2, p is 0.25, and so now the probability is 0.3326 from my CDF table. And to finish the problem, I have to do 1 minus 0.3326, and I get the probability 0.6674. So there's about a 67% chance that you'll get a photon 3 or more times out of 13. The next question says, what is the probability of detecting a photon between 4 and 7 times? And I should be a little bit more careful about how I say this, because if I say between 4 and 7, it's not super clear whether I mean to include the 4 and include the 7, or not include the 4 and not include the 7. So I'll make sure on your test that it says it really clearly whether or not I want to include the 4 and the 7. But let's say this is inclusive. We're including the 4 and 7. And we'll work the problem this way. So this is talking about the probability that x is between 4 and 7. So it's the probability that 4 is less than or equal to x, and x is less than or equal to 7. And this is the tricky part. You got to be able to recognize that the probability of getting x between 4 and 7 is the probability of x being less than or equal to 7 minus the probability that x is less than or equal to 3. Because less than or equal to 7 is all of the outcomes 0, 1, 2, 3, 4, 5, 6, 7. So we need to subtract away the outcomes 0, 1, 2, 3. And that way we're left with only the outcomes 4, 5, 6, 7. Does that make sense? Good. And this time I've got 2 CDFs that I've got to look up. I've got to look up the CDF where k is 7 and the CDF where k is 3 so that I can then subtract those. So the CDF where k is 7 looks like it is 0.9944. And then the CDF where k is 3 is 0.5843. So then I subtract 9944 minus 5843 is 0.4101. Next, what does the distribution mean? Well, this is a binomially distributed random variable, and so you should have this formula memorized. This is n times p, which is going to be 13 times 0.25, and 13 times 0.25 is 3.25. Nice and easy. What is the distribution median? That's when we take n times p and we round it. So 3.25 rounded is going to be 3. What is the distribution mode? That's going to be what I get if I round down and multiply n plus 1 times p, right? Yep. And so to get the mode, we're going to round down after doing 14 times 0.25. And 14 times 0.25 is going to be 3.5, but I'm rounding down, so that's going to be 3. The variance is n times p times 1 minus p. So that's going to be 13 times 0.25 times 0.75. And that's 2.438 or so for my variance. And then the standard deviation is just the square root of the variance. So in your calculator, take the square root of 2.438, and you should get 1.56-ish. So hopefully that's the easy part, right? You've already written down the formulas on your page. If you haven't, go back later, look up my lecture notes from the website, and copy those formulas down onto your page. You bring that page with you to the test, and so you know how to use the formulas. The hard part, I think, maybe is just knowing how to answer these probability questions, because it's not always as easy as using a formula, and it's not always as easy as looking up the CDF tables. Sometimes you have to deal with that complement rule, and sometimes for these between questions, you've got to subtract things. So let's try to do some more examples in the next 20 minutes that we've got together. Suppose you are the afternoon manager at Taco Bell. And you typically expect to see 20 cars go through the drive-thru during the first hour of your shift. So now for that first hour of your shift, what's the probability of seeing 0 cars? This is going to be a Poisson distributed random variable, because this should remind you of fishing, like where you're fishing and you're sitting out there and you're waiting to see how many fish you're going to catch by the end of the day. It's an analogous situation. You're sitting in the Taco Bell. The cars are kind of like fish. Maybe they come, maybe they don't. But it's a discrete random variable that you're counting as some time passes. And we have an expectation. We expect to see 20. But we're not guaranteed to get 20 every hour. It's going to still be a random number. So what's the probability of seeing 0 cars? That is the probability that the outcome is exactly 0. So that's going to be the probability mass function, this time of the Poisson distribution, where lambda is 20 and k is 0. So that will be e to the power negative lambda times lambda raised to the power k divided by k factorial. So you get e to the power negative 20 times 20 raised to the power 0 divided by 0 factorial. Your calculator can tell you what e to the negative 20 is. There's even a special button that says e to the x. It's right above the natural log button, so you have to hit second and then ln. And then you get e to the power, you type in negative 20. That's a super small number, according to my calculator. I don't even know how many zeros that is. 1, 2, 3, 4, 5, 6, 7, 8. 20 to the 0 power is 1, 0 factorial is 1, and so you don't have to multiply or divide by 1. That's the answer there. What's the probability of seeing exactly 20 cars? Again, this is the Poisson PMF, where lambda is 20 and k is 20. So that's going to be e to the power negative 20 times 20 raised to the power 20 divided by 20 factorial. So in my calculator, I type e to the power negative 20 times 20 raised to the power 20 and I get a very large number. I get a very large number. It's like 2.161 times 10 to the power 17. What is 20 factorial? And now I'm thinking I don't even have I don't even have a factorial button on this calculator, so this would be kind of a grind to have to type in 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, and I get 2.433 times 10 to the 18th power. So the power of 10s sort of cancel each other out for the most part, except the bottom has one more power of 10, so it's going to be 24.33, and then 2.161 divided by 24.33 is 0.0888. So there's almost a 9% chance. There's a 9% chance that you'll see exactly 20 cars. All right, let's move on to what's the probability of seeing 10 or fewer cars? That's the probability that x is less than or equal to 10. How do I do this? How do I answer every less than or equal to probability? The table, yeah. The CDF table. So lambda is 20, k is 10, and I pick up my CDF table for the Poisson distribution. Lambda is 20, so it's this column. K is 10, so it's this row. And that intersection says 0.0108. 0.0108. Next, I need the probability of seeing 17 or more cars. So I need the probability that x is greater than or equal to 17. How do I do this? Yeah, it's the table, but with one minus. The statistics probability term for this is the complement. The probability that x is greater than or equal to 17 is the complement of the probability that x is less than or equal to what? 16. Very good. And so now I use the CDF table where k is 16 to get the probability 0.2211. And 1 minus 0.2211 is 0.7789. That's the probability of seeing 17 or more cars come through the drive-thru. All right, what is the probability of seeing between 15 and 20 cars? How do I do this problem?
So less than 15, less than or equal to 15. And then the greater than or less than 20.
Yeah. If I start by asking what's the probability that x is less than or equal to 20, this gives me the probability that x is 0 or 1 or 2 or 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. But I don't want all of those outcomes. I only want the outcomes 15, 16, 17, 18, 19, 20. So I'm going to have to subtract away. And I made a little mistake here. What's my mistake? I should make this a 14. So that way I don't accidentally get rid of 15. All right, and then I just have to look up two numbers from my CDF table. One where k is 20, and the value where k is 20 is 0.5591. And then I look up the value where k is 14. That's 0.1049. And then 5591 minus 1049 is 4542. So there's a 45% probability of seeing between 15 and 20 cars. And those are the hard problems. Everything up next is pretty easy. You just have to have the formula written down on your notes page and then plug the stuff into the formula. Like, what does the distribution mean? Well, that's just lambda. That's just my expectation. What is the distribution median? I'll tell you, it's probably 20 for the Poisson distribution. But we'll go ahead and use the exact formula, which says round down lambda plus a third minus 1 over 50 lambda. Where lambda is 20, so this is 20 plus 1 over 3 minus 1 divided by 50 divided by 20, and that is rounding down the number 20.33, which is of course 20. Yeah. In your calculator, if you want to do 1 divided by 50 lambda, you would type in 1 divided by 50 divided by 20. That will give you 1 divided by 1,000.
So 50 times 20 or is it dividing by lambda?
Well, so that's the thing. Your calculator does everything in order of operation. So if you do this in your calculator, it will give you the correct answer.
If you put 50 times 20 in the parentheses, will it be the correct answer?
Yeah, that's true too. If you do this, it will give you the correct answer. But if you do 1 divided by 50 times 20 and you forget your parentheses, then that is the wrong answer. What is the distribution mode? Let's go and check. What is the formula we'll have written down for the Poisson distribution? It's you take lambda and you round it down. Well, our lambda was already a whole number, so there's no rounding we have to do. The mode would be 20, rounded down to 20. The variance was also just lambda, and the standard deviation is then going to be the square root of the variance, and the square root of 20 is 4.47.